In this video, we're going to take a look at how we can use the TI-84 or a similar graphing calculator to deal with probability distributions and the types of problem that we've seen throughout Chapter 6 here. So the first problem I want to look at is this one up here. And these are two separate problems. So this is a discrete probability distribution that I've got written right here. This is the same set of numbers that were related to the problem involving number of siblings that was in the video that we did for section 6.1 on random variables. So we're asked to find the expected value and the standard deviation of this following discrete probability distribution. So we've got this generic probability distribution. To find the mean and standard deviation of this, what we need to do is go into our calculator. So I've got it turned on, and I want to hit the stat button and edit some data. So I've got my two lists here that I'm going to enter my data in. In the first list, I want to enter the data corresponding to the x that we've got here. So I'm going to enter the 0, 1, 2, and 3. So I've entered now the 4 values corresponding to the values of the random variable itself. Then I want to go over to the other list, L2, and in that list I want to enter the corresponding probabilities. So the one that corresponded to the 0 was 0.3. So there I'm going to do 0.3. For the next one I want 0.35. Then I want 0.25. And lastly 0.1. So now I have a table in my calculator that looks almost identical to the one that I've got here. I've just got this one oriented kind of horizontally, whereas these are going down vertically. But each one of these values of the random variable has the corresponding probability associated with it right across from it. Next thing I want to do to compute all the statistics is the same way that we computed basic statistics back in Chapter 3. I'm going to hit the stat button, and I'm going to go over to the calculations. So I'm going to right click over to the calculations, and I want to compute one variable stats again. So I'm going to hit enter on one variable stats. Here I'm going to do something slightly different than what we did before. For the list, I'm going to leave that as L1. That's the list where the 0, 1, 2, and 3 showed up. In the frequency list, I'm going to put the list where I wrote the associated probabilities, because if you think about it, based on the description that we had in that video, you can really think of these as how frequently each of these various outcomes occurred. And that's what this is meant to indicate. It is the frequency list, meaning it lists the frequencies of each of these other outcomes. So I entered those into L2, so I'm going to hit second 2 to get the L2 option entered in for that list, and go down to calculate. So again, in where I've got list, my first list, that has all of the values of the random variable. For the frequency list, I have the list of the associated probabilities. Now I'm going to hit calculate, and it will spit out the values of interest. So first thing it spits out, so what I've done is, again, I've hit sort of stat, gone to the list of calculations, and I'm doing one var stats with L1 comma L2, where I've entered this stuff into L1 and I've entered all of these into L2. And that spits out the values that I'm interested in, what we call mu sub x. In this case is what's listed as our x bar, it's our mean, and it is 1.15. That is the same value we found doing it by hand in the previous video. And similarly, I've got the standard deviation listed right here. So I've got sigma x. That is much harder to compute by hand, but we've got the value very easily on the calculator. It's about 0.963. We'll call it good enough, approximately. And so that is how you would use the graphing calculator to compute the mean and standard deviation of a sort of generic discrete probability distribution. How do we deal with a problem like this one down here? So let me scroll down and look at this one. Let's get it all on the screen at once. There we go. Okay, so this one says a basketball player is an 84% free throw shooter. In a given game, they shoot 10 free throws. So this is a case where my hope is that we can use the binomial distribution to solve this type of a problem. I want to go through and think about what's going on here. So the hint that this is a binomial distribution, possibly at least, is the fact that we are repeating a basic probability experiment multiple times. In this case, they're shooting a free throw 10 times. And every time they shoot the free throw, the assumption is it has an 84% chance of going in. So let's just go through the 5 conditions associated with the binomial probability distribution to just make sure that this meets those conditions and argue for or against it. So the first condition for a binomial probability distribution, I'm not going to write them all out here, but the first condition in a binomial, the first condition in a binomial probability distribution is that we have a fixed number of trials, which we absolutely have right here. We have 10 trials. So condition 1 is met. The second condition says that we can only have 2 possible outcomes, success and failure. In this case, free throw outcomes are naturally split into those 2 outcomes. A make is a success, a miss is a failure. And so I'm going to let my random variable x, so as long as I let x, my random variable, be the number of made free throws, the number of successes, we've successfully checked off both the second requirement and the 5th requirement. So made free throws. So now it comes down to conditions 2 and 3, which were always the tricky ones to look at. Condition 3 says, is the probability of success the same for every trial? And 4 says, are the trials independent of one another? And this is a point where it becomes sort of a bit of an argument. Some people believe in hot streaks in sports, where if you see a shot go in, you're more likely to make your next shot. They've actually done some statistical analyses, and largely that's a myth. In general, when you see a hot streak in sports where somebody is either consecutive games with a hit in baseball or number of shots made in a row in basketball, turns out those things happen with the exact same probability that we would expect them to happen totally by chance. So there's some evidence kind of either way, but in this case, we're going to assume, so one of the assumptions we're going to make is that indeed hot streaks are a myth. Every time this person shoots a free throw, it has an 84% chance of going in. So that is going to be our assumption here. With that in mind, we will also assume that our trials are independent, that making my last shot has no bearing on whether I'm going to make or miss my next shot. And again, this is something people argue both ways, but we are assuming, so we are going to just say, let's not have this argument, let's just assume that these trials are in fact independent. And so I mentioned before that these things go together, the third and fourth point, independence of trials and the probability always being the same. And let me give you one example of where those 2 points are different. What if we had, instead of one player shooting 10 free throws, what if we had 10 individual players each go shoot 1 free throw? Well, we would still have a fixed number of trials. It'd still be 10. We could still have only 2 outcomes, success and failure, and we could still define X to be the number of successes, so the number of made free throws of this group. And we would still have that the trials are independent, that whether or not the last guy made his shot has no bearing on whether I'm going to make my shot. But we will fail to satisfy the third criteria, which is that the probability of success has to be the same for every trial. Because I have a different probability of success when I shoot a free throw compared to the person that went before me and or the person that's going to go after me, right? I probably have a 10% chance of making my free throw, whereas one of these NBA players has something like this, like an 84% chance of making their free throw. So all the conditions are met in that case, except for condition 3. And so this is one example of a distinction between the trials being independent and the probability always being the same. We'd seen that those often went hand in hand, but they don't always go hand in hand. So that's one example. Okay, so back to this problem in particular, where we're not having 10 people shoot free throws, we're having one person shoot free throws. I want to figure out what is the probability that they make exactly 8 shots, what's the probability they make 8 or fewer shots, what's the probability they make more than 8 shots, how many shots do we expect them to make, and what's the standard deviation of the number of shots that they'll make. So all of these questions I want to be able to answer, and we are going to be able to do all of these relatively easily. So let me just remind you, the formula for probability, binomial distribution probability, is P of x equals ncx p raised to the x 1 minus p raised to the n minus x. And I said this formula, while it's great to remember, and we kind of went through and talked about the different pieces a little bit, in practice, we're just going to compute this whole thing on the calculator. But it requires 3 pieces of information. We need to know n, p, and x. These are the values that we're interested in. So n is the number of trials. For us, it's 10. P is the probability of success for a single trial. For us, if this person makes 84% of their free throws, that probability of success is going to be 0.84. And then x is the value of interest. In this case, in part A, we're interested in what is the probability they make 8 of their free throws. So in that case, I'd be interested in x being equal to 8. So these are the values that I'm going to use. To do this on the calculator, I will again come over here, turn the calculator on. Let me clear and get back to the main screen. So we're back at the main screen. This is the first time that we're not going to use the stat button. Instead, we're dealing with a binomial distribution, which is a type of probability distribution. And so we are going to use the distributions button on the calculator, and it's right here. It is the second option, and in this picture written in kind of in light blue up here, the second option of the vars button. So I'm going to hit second vars, and it's going to give me a list of a bunch of distributions. We've got normal distributions. These ones that involve the t down here, these are t distributions. This weird looking x squared thing is called the chi-squared distribution. So there's a bunch of different ones. And I'm going to scroll down until we get to these ones, Binompdf and Binom Cdf. The PDF and CDF stand for 2 different things. Binom, obviously, hopefully, stands for binomial. PDF stands for probability distribution function, whereas CDF stands for cumulative distribution function. And I'll show you when we're going to use which in these problems. In this case, if I'm wanting to answer part A, what is the probability they make exactly 8 of their 10 free throws? I'm going to use PDF. I want to know the exact value. So I'll select Binompdf. I will plug in, this will generally be empty for you guys, but if it's not, just type over it. So I'm going to do 10.84 and 8. These 3 numbers that I'm entering match these 3 numbers right here. So the number of trials is what we called n, it's 10. This lowercase p right here is the probability of success, that was our 0.84. And the x value is the value that we're interested in. For us, that was 8. So I go through those, hit paste, and hit enter, and boom, it gives me the probability. So the probability of making exactly 8 shots, it turns out that this probability is about 0.28, let's round it to 3 decimals, about 0.286, if I round that 5 up, which we need to round it up. Okay. If you have an older calculator, this is what you would enter. You would enter, again, so some calculators don't give you that menu option that I just showed you. If you have an older one, it would be Binompdf, and then you need to enter n, p, and x in that order. So 10, 0.84, 8, and then close your parentheses. And that will spit out 0.286, the same number that we just got up here. Okay, so that's an example of how we use Binompdf. We use Binompdf whenever we're interested in an exact single number outcome. So exactly 7, or exactly 8, or exactly 9 shots. We would use PDF. But If we're interested in 8 or fewer, this means what we're really interested in, what is the probability that they make 8 of their shots, or 7, or 6, or 5, or 4, or 3, or 2, or 1, or 0. And in that sense, you can think of this as it's the combined cumulative probability of all of those individual values. 8 or fewer includes all of those different values. This one is going to require us to use the CDF option. So I'll do the exact same thing, but I will select CDF. So I will hit second vars to get into my list of distributions, and I will scroll down, and instead of selecting PDF, I will select CDF. Hit enter. And again, here's what it'll normally look like if you don't have data in there already. So how many trials? Again, 10. They were shooting 10 free throws. The probability of success is 0.84. And the X value, the value of interest, is still going to be 8. But when we do CDF, it will now do everything up to and including the number that we enter here. And that's exactly what we've got here. When we say 8 or fewer, we mean anything, any number up to and including 8. And I will go ahead and hit paste and hit enter, and it will spit out the combined probability of all of those outcomes. So it's 0.492-ish. We could individually have done Binompdf with x equals 0, Binompdf with x equals 1, Binompdf with x equals 2, 3, 4, 5, 6, 7, and 8, and then added all of those up to get this probability, but this just did that for us. So in this case, we want CDF whenever we're doing up to and including a given value. So this is if we want exactly a single value, this is up to and including that value. So you can think of this as like an equal sign, and this is basically a less than equal sign. Anytime you have a less than equal sign, you would use CDF. What do we do when we're interested in the probability that they make more than some certain value? Well, in this case, there is no special function on the calculator. There's not a third option that gives us a greater than option. So what we have to do here is use the rule of complements. If I want the probability that the number of shots they make, that x is greater than 8, because that's what's being asked. What's the probability that the number of shots they make is greater than 8? Well, that's the same as 1 minus the probability of the complement. What's the complement of greater than 8? So we've got 0 up to 10 here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me put the 10 there and shorten this a bit. Here's all the different numbers they could make of free throws, right? They could make any one of these values. And we want the complement of greater than 8. So first I need to figure out where greater than 8 is. That dividing line is going to be right here between 8 and 9. So everything over here, this is all the values of x that are greater than 8. And so this must be the complement. And that is all the values of x that are less than or equal to 8. So these two things must be complements. So if I want the probability that x is greater than 8, I can find that by doing 1 minus the probability that x is less than or equal to 8. And luckily, we just found the probability that x was less than or equal to 8 right here. So this number right here, which I guess I'm trying to sneak in here, is going to be 1 minus that 0.492, which I can do over here, 1 minus that answer that we just found, and it's going to be about 0.508. So that is the probability that this person makes more than 8 of their shots. Lastly, when we come down to these bottom two, again, because it's a binomial distribution formula, so for part D down here, let me just rewrite it. If we want the expected value of the number of made shots, again, that's the same thing. I can use either of these symbols. You don't need to use both the way that I'm doing. You don't have to use both. You can pick one or the other. But it's equal to just n times p. Remember that formula. Basically, it's saying how many shots would we expect them to make? Well, they took 10 shots. they make 84% of their shots. I expect them to make 10 times 0.84. I expect them to make, on average, 8.4 of their shots. 84% of the shots they make, I expect them to take. So on average, I expect them to make 8.4 shots. Again, they can't actually make 8.4 shots in a single run of this. But if we had them shoot 10 shots, record how many they made. Had them shoot 10 shots, record how many they made. Had them shoot 10 shots, record how many they made. Did that over and over and over again. Then in that particular case, if we averaged all those results, we would expect to see 8.4 if this person is indeed an 84% free throw shooter. And lastly, if we want the standard deviation is sigma x, and that is the square root of np times 1 minus p. And that is going to be, again, we're not using the calculator for anything more than calculations. I was able to do this in my head. We could have done it over here, 10 times 0.84. And it gives us the 8.4 that we're going for. But we're done with the special functionality of the calculator. These were just plugging in and doing kind of regular calculations. So in this case, this one's going to be, we already figured out what n times p was. It was 8.4, so let me just write that 8.4 in. Times 1 minus p, so 1 minus 0.84. 1 minus 0.84. So I can do this all in one big step. I just need the square root button first. So the square root button is the second option of this button. So I'll hit second that to get my big square root. I've got 8.4 times, and let me put this in parentheses, 1 minus 0.84, and close that parentheses. And hit enter, and it spits out a number, and that number is about 1.16-ish. I guess we can do it 3 decimals. Did everything else 3 decimals, so 1.159-ish. And it says that on average, they're going to make about a little more than one shot more or less than this. So most of the time they're making more like 9 shots or 7 shots. On average, they're about a shot off from the 8.4. It tells us exactly how consistent this person is when they shoot their free throws. So that is how we can do both of these types of problems. This is the stuff from section 6.1. This is the binomial distribution stuff from 6.2. So just a generic discrete probability distribution up here, and a binomial probability distribution down here. And this is how we can use the calculator.